Okay, good morning. We will get started with magnetic fields. So this is new material that will not be on the exam Friday. This is all new material not on Friday's exam. I'll send out an email. Like 9:15 or something. I forgot what I said. Try to give you a little more time, but I want to try to end it a little early also, because I have another class back to back that has an exam. Okay. Magnets. We've played with magnets, hopefully. So we know a little bit about magnets. We know that they have two poles on them. And someone came up with north and south. And we know that like poles repel. And opposites attract. So these two would feel a force in this direction, and these two would feel a force in that direction. Okay. And the interesting thing with magnets now, we've been talking about fields and electric fields, gravitational fields. Now we're going to talk about magnetic fields. And one of the interesting things with magnets is that we can all of a sudden, for the first time, get a visual of the fields. And the reason is that any little iron atom, which we will learn soon, is a magnet. An iron atom is magnetic, it's a magnet. And a little tiny sliver of iron is a magnet, and it will try to align itself with another magnetic field. Magnets try to align with magnetic fields. They feel a torque in the magnetic field, and they turn and try to align themselves with the magnetic field. And so because of that, we can sprinkle little pieces of iron around a magnet, and they will align themselves with the magnetic field. So let's take a look at that real quick. So this is a bar magnet, north and south pole. And the magnetic field lines look like this. They originate on north poles, terminate on south poles. So here we have a north and a south. So the magnetic field lines go from the north to the south. No lab this week. Okay, so that's north and a south. And here we have two north poles. And so the field lines come out and then go up and down towards infinity, right? They repel each other. Okay. So if we draw them in, field lines. I don't like this pen. My pen died. That one goes off to infinity. That one comes in from infinity. This loops around back to here. And this does something like that. Okay. That's kind of what we saw. North, south, straight across. And north, north. Does one of these. Okay. And if we take a magnet with a north pole and a south pole, and we break it down the middle, what do we get? All the north poles on one side, all the south poles on the other side? No, we don't get that. Two smaller magnets, and we break this one in half. And we get a north and a south, right? And a north and a south. And we can keep breaking that up. And we always get and in case you don't believe me, here's a magnet, north, south, north, south. So these are going to attract, right? Now, broke it. It's better with sound effects, isn't it? So what did we get rid of all our south poles? No, they still attract. They still attract. Let's do it again. See if we can get rid of those south poles. Okay. They still attract, still a south pole. No matter how small, you can break that up until it's just a single atom of iron, and it would still have both a north and a south pole. So yeah, it's so we kind of say, even though it's not true, we kind of say that all magnetism comes from moving charges in some way or another. That's not really true, but that's sort of what we say. So some particles, like electrons, have a magnetic moment, right? An electron is a little tiny magnet with a north pole and a south pole. And the way to visualize this, which I don't know why we really, physicists get themselves into corners sometimes, but if you, well, first of all, you don't know this yet, but you will very soon. A current, a moving charge fills the space around it with a magnetic field. And so a current in a wire is a bunch of moving charges, fills the space around it with a magnetic field. And if you have a loop of wire and a current in that loop, it acts like a little bar magnet. It makes the same magnetic field as a little bar magnet. Now, if an electron was a ball of charge, it's not, but if it was, if you could imagine an electron is a sphere that's charged, like the Earth, a sphere that's charged, and it spins on its axis like the Earth, then each charge would be going around in a circle, creating a magnetic field that made it look like a bar magnet with both a north and south pole. Now, an electron is not a little ball of charge that spins on its axis like the Earth does, but you can kind of imagine, even though it's not true, you can kind of imagine how you could get an electric field that way. Now, to make matters worse, we call that property spin. So physicists are always like, electrons don't spin. Well, why did you call it spin then? You know, I don't know. They get themselves into problems. Anyway, an electron has a magnetic moment. An electron is a tiny bar magnet with a north and south pole. When electrons line up in atoms to form the structure in an atomic structure, their spins cancel out. So if you have an even number of electrons, their magnetic moments will cancel out. If you have an odd number, you may end up with a net magnetic moment due to the electron spin. And then there's some contribution to the magnetic moment of the atom from the orbital motion. There's a cloud of electrons around the atom, and that motion probably contributes to the magnetic moment of the atom also. So some atoms actually are tiny magnets. They have a magnetic moment, and iron is one of them. All right, the Earth has a magnetic moment. We have magnetic field lines that fill the space around the Earth. which end is the it's as if, right, the Earth sort of acts as if there's a big bar magnet inside there, right? Which end is the North Pole and which end is the South Pole? South is north, that is correct. This is a magnetic North Pole. This is a magnetic South Pole. And the reason we call this the North Pole man, cannot get used to this stylus. The reason we call this the North Pole is because the north end of your compass needle points that way. So if you stand here and you hold a compass, the north end of the compass, which is a north magnetic pole, points in this direction. So we call this the North Pole of the Earth. But it's a magnetic south pole. The North Pole on your compass is attracted to it. You had to pick one or the other. I don't know how they made the mind up their minds. You either say that it's called the North Pole because the North Pole of your compass points to it, or you go the other way, right? How can you tell it's a South Pole? It's a good question. There are some things you can do, we will learn right now, where you can look at forces on particles and you would know what direction the magnetic field line points. So you would know that the magnetic field line originates on north poles and terminates on south poles. And that's just somebody picked, right, and said, let's call it that way. So let's call the north end of the magnet where the magnetic field lines come out, and the south end where they terminate. And then from other tests, we can determine what direction the magnetic field points. So let's talk about forces. And that'll show you that we can detect the direction of the magnetic field. Okay, let's have a magnetic field. We use B for magnetic field. And let's put a particle over here. Charged particle, Q, sitting there at rest in our magnetic field. It feels no force. Now let's take that particle and give it some velocity in the same direction as our magnetic field. It feels no force. Now let's take that particle and give it some velocity perpendicular to the magnetic field. It feels a force. We'll call it F sub B, the magnetic force. So what do you think the magnetic force may depend on? It's going to depend on the orientation. I've sort of made that clear or hinted at it. What else might it depend on? the velocity. If it's sitting at rest, it doesn't feel a force. If it's moving and it has some component of velocity perpendicular to the magnetic field, it feels a force. So the velocity, the orientation, what else? It's going to depend on the magnetic field, right? And it's going to depend on what kind of particle is this? Charged particle, Q. So those are the things we expect it to depend on. If it's a charged particle interacting with the field that gives us a force, then the amount of charge is going to have an impact, right? And the field strength is going to have an impact. A charged object will not move due to a magnetic field. Another magnet will move, but not a charged object. So what do we get here? We get the force is equal to Q V cross B. And we get the direction. Let me just get rid of this. We've got that now. Direction comes from the right-hand rule. This is a cross product, a vector cross product. You put two vectors in, you get a vector out. Direction comes from the right-hand rule. So in physics, we have a lot of right-hand rules. You have to think about what's causing us to do the right-hand rule, and that helps to figure out which one it is. Most of them come from the right-hand rule. So if you understand that the equation has a cross product in it, you know immediately what right-hand rule you're using, and it should be very clear. Some other ones are slightly different, but any equation with a cross product, we use the right-hand rule to get the direction. So let's take a look at that. If vector A is equal to B cross C, then B is this way and C is that way. What I do, I put my fingers in the direction of the first vector, B. So if my fingers point, let's see, B points to the right. So I would do my fingers that way. Then I kind of roll them towards C. I pick the angle that's less than 180 degrees, roll them towards C, and my thumb points perpendicular to both B and C, perpendicular to the plane defined by B and C, and it points in the direction of the cross product, B cross C. So B cross C points toward you, toward the camera. If I'm writing it on paper here, I would say A points out of the page. That means that if I switch the order, what do I get? A is equal to C cross B, using the same C and the same B. I put my fingers in the direction of C, roll them toward B, and my thumb is pointing toward me this time, or away from the camera. And if I was doing it over the piece of paper, my thumb would be pointing into the piece of paper. So A would be into the page. All right, we'll practice some more of those. Units for magnetic field. Tesla. Capital T is the symbol. And 1 Tesla is 1 Newton per Coulomb meter per second, 1 Newton amp meter, and 10 to the 4th Gauss. Or this is the SI unit for magnetic field is the Tesla. The Gauss is a non-SI unit, but people that use magnetic fields all the time like Gauss better because Tesla is a fairly large amount of magnetic field. So most of the time you're not dealing with magnetic fields that are that big. So rather than having 10 to the minus 3, 10 to the minus 4, 10 to the minus 5 next to every number, you just pick a unit that makes a little more sense for what you're using all the time. So they use Gauss as a little more convenient because of the size. Yeah, the company is called Tesla because it's of the work Tesla did with electricity, I guess, right? It's an electric car company. And so Nikolai Tesla did a lot of work with electricity and magnetism and induced EMF and things like that. Okay. Work. Let's talk about work. We love to talk about work done by forces, don't we? So I've got a magnetic field. I'll make it pointing towards the top of the page. Oops, what happened? And we're going to move a particle from A to B. Make it a positive charge. Okay, we're going to move that positive charge from A to B. How much work is done by the field in moving that particle from A to B? Charge Q. If the particle is moving from A to B, where's our formula? There it is. If the particle is moving from A to B, the force is going to be Q V cross B. What direction is V cross B? Right, V is this, oops, why do I keep doing that? V is this way. B is this way. So V cross B is what direction? Out of the page. V cross B out of the page. Okay. How much work does that force do on the particle moving from A to B? Yeah, this is a dot product, right? Work is force dot distance. So what do you get? Zero. Because in order for the force to do work, it has to have some component in the direction of motion. But the magnetic force is always perpendicular to the direction of motion. Makes sense? Magnetic force always perpendicular to V. V is the direction of motion. The force has to have a component in the direction of motion to do work. So the magnetic field, work done by the magnetic field, always zero. Which means, what does that mean? It can't do work on it. It cannot change the speed of the charge. It can only change its direction. Okay, it follows from the formula here. I mean, I know this is a weird formula, right? This, accepting this is not straightforward, right? But once we kind of accept this, once we say to ourselves, okay, this magnetic force is weird. A charged object does not feel a force in a magnetic field if it's stationary. It doesn't even feel a force if it's moving along the magnetic field lines. It has to have some component of its velocity perpendicular to the magnetic field lines. And then the force it feels is perpendicular to both its velocity and the magnetic field. That's just weird, right? That's just crazy. But that's the way it is. Once we accept that, then it follows that the force from the moving charge is always perpendicular to its motion, so it can't possibly do work. Yes, it's accelerating because its direction changes, but its speed does not change. So its velocity is changing because the direction changes. Velocity is a vector quantity. Yes. All right, we have to have some, we have to start dealing with drawing in 3 dimensions. We can't really avoid it anymore. The reason is that if I draw my magnetic field and my velocity in the plane of the page, then my force is going to be perpendicular to the plane of the page, right? Something has to be perpendicular. You've got 3 things that are all perpendicular to each other. Something has to come out of the page, right? I can't draw it anymore. So we come up with this system here. We've got a dot and an X. Sometimes they're in a circle like that. Sometimes they're not. And the dot means it's out of the page. Come on. Oh, it didn't die on me. And the cross means into the page. And the way you remember that is it's like looking at an arrow. If the arrow is shot toward you, you see an arrow coming at you. What do you see? Just the tip of the arrow, just a dot coming toward you. But if that arrow is going away from you, somebody shoots an arrow and it's going away from you, you see the cross feathers on the back of the arrow. So that's how you remember that. So yes, circular motion. It's like circular motion. So if I have a magnetic field into the page, there's my magnetic field. And I have a particle here, and I give it a little push. Let's make it blue. It is going to feel a force. What direction is the force? Yeah, I try not to use up and down. I try to use toward the top of the page, toward the bottom of the page, into the page, and out of the page, because up and down can get a little confusing. Of course, I will slip up at some point and use up and down. So toward the top of the page, V cross B would be toward the top of the page. So that it feels a force in that direction, which means it's going to start moving this way. And eventually, it's going to get to this point over here. There we go. Finally died. It wanted to crash earlier, but there we go. Sharing. You put your fingers in the direction of the velocity, and the magnetic field is into the page. So your thumb, fingers in the direction of velocity, magnetic field into the page, your thumb is going to point toward the top of the page. Your thumb will point this way. Now your velocity is in this direction, and your force is in what direction? V is pointing towards the top of the page. roll your fingers into the page and your thumb should point to the left. So you get circular motion. That means it's very difficult for charged particles to cross magnetic field lines. It's easy for them to go parallel to magnetic field lines because they feel no force then. But if they try to cross a magnetic field line, they feel a big force perpendicular and they want to spiral around the magnetic field lines. One interesting thing that we see due to this effect is the northern and southern lights, the aurora. Charged particles from the sun come towards the earth and they hit that magnetic field and they really have a hard time crossing the magnetic field lines. They start to move in circles around the magnetic field lines. And if they have any component of their velocity along the magnetic field lines, that's where they're going to go. They're going to spiral around. They're going to do this. They're going to end up going spiraling along the field lines like that, or if they have some component of velocity in the other direction, they'll spiral around like that. So we've got charged particles coming toward the Earth from the sun. They get to the magnetic field and they start to move around the magnetic field lines. Of course, what are the odds that those particles will be moving exactly perpendicular to the magnetic field line? Almost nothing, right? They're probably going to have some component of their velocity along the magnetic field line. So when they start spiraling around the magnetic field line, they'll keep moving in that direction, either one way or the other. And where are they going to bombard the Earth? Near the poles, right? So somewhere around the North Pole, you've got all those charged particles hitting the atmosphere, coming in and hitting the atmosphere, exciting the gas molecules in the Earth's atmosphere. When those gas molecules drop back down to their lower energy level, they give off light. And that's the aurora borealis, the northern lights, and the aurora australis in the southern hemisphere looks the same way. You have this sort of halo around the South Pole where those charged particles hit the atmosphere, excite the gas molecules, they drop back down to their lower energy state, and they give off light. It's one of those things, if you haven't seen it yet, add it to your bucket list. Things to see, the northern lights or the southern lights. Sometimes they're not very exciting. I've seen them a couple of times. Once I was looking out at the sky and I thought, boy, it's weird. The clouds kind of look like they're lit up. And then I realized there weren't any clouds. It was perfectly clear evening. It was just, there was this glow sort of coming from the sky. That was the aurora, the northern lights. and then other times it's really fluid, and it's like there's motion, and these colors are almost flowing in the sky. It's quite interesting. I saw them in Alaska.
Professor Frank, if that's the case, the light color in the North Pole and the South Pole is supposed to be different. Is that the case?
No, I think they look the same, because the Earth's atmosphere is made up of the same particles, right?
Oh.
So when a nitrogen molecule gets excited and it drops back down, it gives off a certain wavelength of light. When an oxygen atom gets excited and drops back down to its lower energy, it gives off a certain wavelength of light. When argon or there's other gas molecules that are in much smaller percentages, mostly nitrogen, of course. The atmosphere is 80% nitrogen and about 20% oxygen, but there's other things in the atmosphere too. And they all have their distinct color. So usually you get this greenish color, but not always. You can get pinks and things, but I think it's determined by the atmosphere, not whether it's the north or south.
Sure. Thank you.
Iceland is a good place to see it. Brent saw it in Iceland. So anyway, check it out if you can. And what else? Solar eclipse. Did you see the solar eclipse a couple of years ago? That's a good one to see. There's another one coming in 2024, I think, through the United States, but it won't be hitting the West Coast, but you have to travel to the Midwest or something. But I think it's 2024. There's going to be another solar eclipse in the US. Okay. Why don't we do this? Why don't we take a 10-minute break, and then we'll practice our right-hand rule a little bit. I'll see. I'm not sure how I can do this on video, but do the best I can. All right, so let's take a 10-minute break. I'll pause the video. Okay, we'll practice our right-hand rule a little bit. All right, so what I like, I want you to think in terms of the cross product first, right? The direction of V cross B. So our equation and remember, we're dealing with velocity now. V is velocity, not electric potential. So got to switch gears on that a little bit. So let's take a look at some of these. We've got all right, for this first one, the cross product, what does that do for us? Gives us 0. So the force is 0, no force on this guy. Next one, we've got our magnetic field in this direction and our positive charge moving this way. V cross B, what direction is V cross B? let me, how can I do this? Into the page. So if my magnetic field points to the right and my velocity is up, I have my fingers in the direction of the velocity. I roll them toward the magnetic field, and my thumb points into the page. Okay, so V cross B is into the page, and the direction of the force into the page. Now, why am I splitting them up like this? You're wondering. Now we have a negative charge moving up. What direction is V cross B? Into the page, same as before, right? Same velocity, same magnetic field. What direction is the force on this thing? Let's look at our formula. V cross B is into the page, and then we're multiplying that by Q. So if Q is positive, the force gets its direction from V cross B. If Q is negative, the force has to be opposite, negative of V cross B. You see that? Our magnetic field will stick with our magnetic field in this direction, and we'll have our negative charge and the velocity into the page. What direction is V cross B? So V is into the page. So I point my fingers into the page. B is to the right. So this is a hard one. Into the page, to the right. So my thumb points toward the bottom of the page. V is into the page. I roll them towards B, and my thumb points towards the bottom of the page. V cross B is towards the bottom of the page. That's why I'm splitting it up. I want you to first find the direction of V cross B, then find the direction of the force. Because I want you to start thinking in terms of V cross B and then negative particles. So this was, what did I just say? And of course, the charge is negative. That's going to flip this 180, and we get the force is to the top of the page. Okay. Let's do this one. We've got our same magnetic field. V equals 0. If V is 0, V cross B is 0. And the force would be 0. No force on that guy. How about this one? Let's have our magnetic field going up in an angle like that. And we'll have our particle going this way. V cross B is out of the page. Doesn't matter that it's at an angle like that. And it's a positive. So the force is also out of the page. Let's have our magnetic field into the page. We'll have a positive charge moving this way. Do one more. V cross B towards the top of the page, and it's a positive, so the force is also towards the top of the page. And how about B coming out of the page this time? And let's make it a negative particle going that way. Okay, so B is coming out of the page. V is going towards the top of the page. So V is going towards the top of the page. B is coming out of the page. So my thumb points to the right. V cross B is to the right. V cross B is to the right. This is a negative. It's going to flip it 180 degrees. The force will be to the left. V cross B is to the right. And to the left. Did I get that correct? The right and left. Okay, I think that's correct. All right. These are for moving charges. Charges moving in magnetic fields. So what is a current but a bunch of moving charges, right? So we have a current carrying wire, have some region filled with a magnetic field. Got our current carrying wire. What direction is the force on my current carrying wire? So let's think about this for a second. Current So if positive charges move, when we see this symbol, what does it mean? It means we have positive charges moving in this direction, right? That's what current means if positive charges move. So what direction is our force? Our magnetic field, B is in, out, B is out, right? We have a wire here carrying a current I. If positive charges are moving to the right, what direction is the force? Toward the bottom of the page, correct. Now, what happens if that's not what's going on? So a current in this direction really means a negative charge is going that way, right? If a negative charge is moving the other way, V cross B is toward the top of the page, but it's a negative charge. We get the same direction. Doesn't matter whether negative charges are moving to the left or positive charges are moving to the right, we get the same force. B is out of the page. So the velocity for the positive charges moving to the right, this is a positive charge moving to the right. Positive charge moving to the right. B is out of the page, so my thumb points towards the bottom of the page. It's always amusing to watch you during an exam, doing your right hand rules, twisting your hands around. Okay, there is one trick to using the right hand rule. You have to use your right hand. If you're like me and you're right-handed and you're feverishly working a physics problem and you don't want to take the time to set the pens down to do the right hand rule, that's just a disadvantage you have for being right-handed. the lefties have an advantage there. They can keep their pen in their hand, do their right hand rules, and keep writing. Use your right hand. You could actually use your left hand for negative charges, but there's a lot of right hand rules to kind of keep track of. So I think it's simpler just to look at the equation. Oop, there's my equation. Look at the equation and say, I've got a cross product. I always use my right hand for a cross product no matter what. And then, oh, Q is negative, that flips at 180. But if you like to use your left hand for a negative charge, that does work. Okay, so we're okay with this one. Positive charge is moving to the right, negative charge is moving to the left. Turns out, doesn't matter. The force is in the same direction. There is a subtle difference. We'll talk about that soon. But for now, same thing. Force is identical. So let's jump back up here. What direction is the force? It is toward the bottom of the page. And the formula, I'm sure the book works it out for you. You have to convert Q and V into an I. But anyway, you end up with this formula. The force on a current carrying wire is I L cross B. And it's really funny. Physicists bend over backwards not to make current a vector. I don't know why. But I is not a vector. L is a vector. L is the length of wire in the magnetic field. And what direction does L point? In the direction of I. But usually I just think in, my old equation, V cross B, it's a positive charge moving to the right, and I get I use my right hand rule. Seems that's like it, yeah. Okay, so now we have an equation for a current carrying wire in a magnetic field. Should we do a few more? Let's do so we've got a magnetic field. We've got a current. We've got a magnetic field. We've got a current. Okay, how are we doing here? First one. There is no force acting on that wire. It's in the direction of the magnetic field. B. Into the page for B. C then would be out of the page. Let's have this one go in. Okay, how are we? D. So D, you're going to point your fingers in the direction of the current into the page. Roll them to the right, and your thumb points toward the bottom of the page. E is just the opposite. The current is coming out of the page. B is to the right, so your thumb points toward the top of the page. There are other methods. Some people use the 3 fingers like this at orthogonal directions. Then you just have to remember which one is the first vector, the second vector, and the cross product. Some people use like the palm of your hand, your fingers and your thumb, and then the palm of your hand is the cross product. I don't know. I just do I roll my fingers and my thumb points in the direction of the cross product. Use whatever you like. So this is just the opposite. This is to the top of the page. How about this one? Yeah, it's going to have kind of a funny angle on this one, right? And G is towards the top of the page. And how about having B coming out this time? And I. Yeah. To the right. Okay, so practice those. You want to get good at right-hand rules because, I'm assuming you know that part of it and we're testing you on other things. So get good with the right-hand rules, practice it a little bit. Let me know if you're having any issues. We'll do the best we can with video. Now, sometimes our wires don't take a nice direct path from one point to another. We're going from A to B. Doesn't matter where B is. Let's just put a point somewhere over here. And our wire does something like this. What we can do in this case is draw a straight line path with the same current. And it turns out the force is the same because all the motion perpendicular from the charges, the current, the motion of the current, the motion of the charged particles in the wire, perpendicular to that straight line path from A to B, cancels out. All the motion perpendicular cancels out because it has, whatever goes up has to come back down, right? It has to be on that line eventually. If it starts on the line at A, it has to be on the line at B. So all the motion perpendicular cancels out. For every velocity away from the line, there's one toward it. And the only thing that matters is the velocity along the direction of the line. That's the same thing as if we'd just taken a straight wire between points A and B. So the force on this wire is just equal to the current times the straight line path, L prime, times B, where this is L prime. Let me, I'm running out of colors here. I'll use this. That's L prime. Okay. You can just take the straight line path. So what's the force on this thing? A current loop. This one is going to be 0. 0. And you could see that by breaking the loop up into sort of two halves, right? The lower half you've got your lower half doing something like this, and your upper half, I'm going to get rid of this thing in the center here. Hold on. And we already said that we can replace this curved line with the current, same current in the straight line path between these 2 points. So we can replace that with this one. And we can replace the upper one. We can replace the upper one let's use blue. We can replace the upper one with this guy. And you can see that those two are going to cancel out, right? F net is 0. No net force on a closed current loop. In a uniform magnetic field. Okay. But what is there? Let's do this. Let's be a little more. We'll have our magnetic field. Our current carrying what direction is the force on the top? There is no force, right? On the right side. Actually, I'm just going to call this the force, not the direction of the force. Force. F sub b. And what direction? Out of the page. You see that? And on the bottom, and on the left. You okay with this one? And when we add these up, add them up, what do we get? We get F net is equal to 0. No net force. But what is there? Picture that current loop. One side, there's a force out of the page. The other side, there's a force into the page, away from the camera. One side has a force toward the camera, one side has a force away from the camera. What's this going to do? They cancel out. There's no net force. But what is there? Yes, there's a net torque. This thing is going to rotate. All right, here's my loop of wire. Top, no force. Right side has a force toward the camera. Bottom, no force. Left side has a force away from the camera. Those two forces are equal and opposite, so there's no net force on my loop, but they're not acting at the same point. One is pulling toward the camera, one is pushing away from the camera. What is this going to do? It's going to rotate until it gets to this point. And then at this instant, there's no torque, right? One is pulling toward the camera, one is pulling away from the camera. But if my loop has inertia and it starts to rotate, it will, even though the torque goes to 0 at this instant, it will continue. And then the torque will be in the opposite direction. It'll slow it down. And then it'll rotate this way. All right, let's figure out what the torque is. We'll go through this with a little more detail. So we've got our magnetic field. We've got our loop of wire, and I'm going to make it, call this distance the length. Oops. I think I'm better off with a thicker pen here, don't you think? We'll call this L. And we'll call this one W. Is that everything we need? I think that's everything we need. So again, forces real quick. Top, 0. The right-hand side is going to be I times L times B out of the page. Okay. The bottom, 0. And the left is going to be I, L, B into the page. We add them all up, 0. But let's find the torque. I'm going to switch. This is a side view here we're looking at. I'm going to switch to a top view. So looking down, put your eye at the top of the page, looking down, you see the same magnetic field, but you're looking down on that loop now, just looks like a rod. And on the left-hand side, what's the current doing? Coming toward you. And on the right-hand side, it's going away from you. Maybe I'll draw that a little bit bigger. What direction is the force on the left-hand side of this loop? We said it was into the page, remember? But if you're looking here, if we moved our eye up to the top, into the page is now toward the top of the page. But let's just think about it. The current is coming toward us. B is to the right. So my thumb points in this direction. And on the opposite side, it's going to point this way. And this distance, it's rotating about its center point, right? And so this distance is half of the total width. Can't really see that very well, can you? W over 2. So our torque then is At this instant, this actually is the maximum torque. So it's the force times the lever arm. Plus the other one times its lever arm. And what do I get when I plug everything in? I get I, L, B, W over 2 plus W over 2 is just W. And what is L times W? It's the area of the loop. It turns out that that always shows up here. So this is I times the magnetic field times the area of the loop. Okay, so next time we will continue. We'll find the torque at any given point. Doesn't have to be at this location where it's maximum. Obviously, as this thing rotates, well, we'll get there next time. Okay, I'm going to stop the recording. We've got, I'll stick around for a few minutes, but I'm holding a review session at noon for my other class. And then we've got office hours tonight, and then we'll set up something for tomorrow. I have to switch my office hour tomorrow, probably to an hour later, but I'll let you know what we've got going for tomorrow. Okay.